Is that audible? Yeah, good. Okay. All right, good. Why don't we start in? I wanted to say a few things before class starts. We had the Origid meteor shower, right? Did anyone see any? Right? Yeah, I saw some. Good, good. Right. So I was very pleased by how many people were out there at basically 4:30 in the morning. And the reports are that the peak was actually around 4:15 or 4:20, not 4:33. And in conversations with a bunch of you, I think we were saying that around 4:30 or 4:40, we were saying, gee, it seemed like there were more of them like 20 minutes ago, right? So indeed, the predictions were off by a little bit, but it's great that a lot of you came out. My daughter's third grade teacher even came out, turns out. Is she here today? You know? Anyway, yeah. There we go. All right. Yes, Michael Strange. That's great. So my daughter's now in the 9th grade. But anyway, so that's fantastic. And here's my count. I saw a dozen of them in basically an hour. But I almost overslept the whole thing. I set my alarm for like 3:10, but I woke up at 3:55, and 15 minutes later I was on campus. So I broke some speed limits, but don't tell anyone, okay? Well, I guess I just broadcasted it to the world, but oh well. Now, we didn't exactly see a storm like the Leonid storm of 1966, but considering that a bunch of us saw something like 10 or 6 or 12 or 15 meteors, that's pretty good for a shower which most years is totally obscure. I didn't even know about it, right? In fact, I thought it was the Aquarids at first. It's the Origids. But anyway, so it was better than nothing, and it's probably better than the Leonid storm or shower will be later this semester. And so those of you who saw some meteors probably saw something like this. This is not a photograph from that night. This is a different night. It's a Perseid. And here's a photograph I really like, taken by this guy in Finland, Pekka Parviainen. It shows the reflection of a meteor and a bunch of stars in a lake. Isn't that cool? Anyway, I think that's cool. Speaking of meteors, I saw possibly the best one of my life just 2 weeks ago. During the day, I was actually at Mount Whitney. I was climbing or hiking Mount Whitney. I'm not really a climber, I'm a hiker. So there it is on the right there with the sun in the way, so it's kind of blurry. But there I am on the top of Mount Whitney, okay? So this is just 2 weeks ago. And it's a beautiful mountain range. If you're sitting there at the trail camp looking at about what you're about to go up, it's kind of a scary thought. But we were standing there watching these mountains, and this meteor just, the sun was behind the ridge, but not behind the true horizon. So the sky was still pretty bright. But this meteor went zooming down, and by the time a minute later I fumbled around to get my camera, there was still the smoke trail sort of from it, and you can see actually different wind patterns in the atmosphere. See here, the wind was blowing this way, there it was blowing that way, but this thing basically went down like this, and it was easily naked eye. I mean, it was really bright. If it had been nighttime, it would have lit up the whole sky. So that might be the best one I've ever seen, and we were just sort of staring at this, at this amazing ridge. So anyway, so that was kind of fun. So I'm glad that you saw some meteors, and stay tuned for meteor showers in the future. They're fun to watch, and the Perseids around August 12th, 11th, and the Geminids around December 13th are the two best ones of the year, typically. Occasionally there's one that rises from obscurity, but the ones that sort of you can rely on are the Perseids in August and the Geminids in December. All right, a couple of announcements. Homework 1 is due on Friday. We've said all this before, so you can look at some of the earlier webcasts, and also all this is written in your course readers. The bookstore, by the way, is out of packages, I think, but NEDS has some, and my publisher is coercing the NEDS administration to tear apart some textbook reader packages. So I know some of you still have the textbook but don't have the reader. I think NEDS is gonna cave in. Otherwise, I threatened that we would simply give all the books to the ASUC bookstore next year, and we simply wouldn't deal with NEDS. So then they said, ooh, well, no, actually, we don't want that to happen. So I think they're caving in, but it might not happen today. It might happen tomorrow. In any case, we've put homework 1 on BSpace in case you don't yet have the reader, but you should get the reader soon. Okay. Please, you're welcome to work with your friends. We encourage you to do so, to discuss the questions with your friends. But in the end, write down the answer in your own words, not too similar to the words of the buddy you were working with, okay? Go out of your way to choose slightly different wording, okay? Because the graders are going to be looking for wording that's too similar, and you will be penalized for plagiarism, basically, although we encourage you to work with people and to go to talc and stuff like that. But any form of copying or plagiarism is not going to be allowed. Okay, a couple of more announcements. Again, students in Monday sections don't have to go to a discussion section this week, but they are welcome to do so and to benefit from the wisdom of the GSI. Okay. Finally, I thought I'd mention this because the deadline is coming up. This is totally optional, but if you want to accompany me and my part of my team of graduate students, researchers, to Lick Observatory, where we will use this 3-meter reflecting telescope, and all expenses will be paid, which basically means a couple of meals and a dorm-like room. It's not like a Hilton or a Hyatt or something. But anyway, if you really want to go and see what real research is like, now we're not going to be looking through a telescope. You're going to be sitting in a boring room looking at computer screens, and I'll want you to be really, kind of entertaining all night and stuff. So you're not going to be looking through a telescope. There are other chances to look through a telescope. But if you want to see how research is done, sitting around with a bunch of computers and electronic detectors and stuff, write me an essay or compose some music or a poem or draw a picture, whatever you like. Do something creative that convinces me that you should be one of the few who is chosen out of this very large class. Now, unless you really want to go, you shouldn't apply, because I might choose you over someone who wants to go a couple of reallys more than you do, if you know what I mean, okay? And so if you only kind of sort of want to go, or you think we're going to be looking through telescopes, then this is not for you. But if you really want to go and see what research is like, I encourage you to submit something, and there are more details on page 9 of the reader. And try to get me something by the end of the day on Monday, September 17th. Okay, now, a few more things. Talc this week, star parties. There was one last night, I think. There will be ones tonight and tomorrow. And then my office hours today and this Friday and Monday are canceled. Now, this is not generally the case, all right? I usually like to talk to people, and I still do. But I have to head to the airport immediately after class today, and I'll tell you why in a minute. Nicholas, the head GSI, will give lectures on Friday and Monday, and I've prepared stuff for him. He'll say it in his own words, but again, it's the stuff that's in the reader, and he will embellish on it and stuff, and so you should definitely come here and show your support. I think he'll do a fantastic job on Friday and on Monday. And I will be back the following Wednesday if the flights are all okay. The reason I need to leave is actually kind of exciting. There's this major award called the Gruber Cosmology Prize. And we have learned that 2 teams, both of which have a big Berkeley component, are the co-recipients of this year's award. And the celebration will be in Cambridge, England, at Cambridge University this weekend and early next week. So I'm taking off for a 7 p.m. flight right after class. I'll tell you more later on what the award is for, but it's sort of for one of what many astronomers and physicists think is one of the major discoveries of the past few decades. And that is that the expansion of the universe is speeding up with time. It's accelerating. Now, the expansion of the universe will be a big topic near the end of this course, and I'll talk about the acceleration and all this in more detail. But just to give you a taste of it, we've known since the late 1920s that galaxies are moving away from one another. But what 2 teams found, and here's one of them, it's part of one of them. This is the High Redshift Supernova Search Team, and there's a bunch of people. Adam Rees was a postdoc working with me at the time that we made the discovery. He's the first person on our team to realize that we had discovered something. And Brian Schmidt in Australia is our team leader, and then there's a bunch of other people, Joker here and stuff like. And then there's another team as well, and I have the distinction of being the only person who was at one time or another associated with both teams, so I'm actually on both discovery papers, but doesn't mean that I get a large amount of the loot. The loot is 500,000, but it's spread over 50 people, and the 2 team leaders get most of it, or half of it. But anyway, so it's not really the money, it's the recognition that this is an important discovery. So there's one team, and the other team is the Supernova Cosmology Project, led by Saul Perlmutter, who's a professor of physics here. and teaches like the physics of music and stuff, and it's a really good class. And, contrary to popular opinion, we're not always at each other's throats, and in fact, it was a spirited and generally healthy competition. Both teams wanted to be first, and both teams wanted to be right, okay? And so if one team was taking into account something subtle and the other team was not, then that other team would look bad in comparison. So what we found was something very extraordinary. We looked at very distant exploding stars, supernovae, of a particular type. They're called type 1As, and I'll tell you about them later. And what we found is that they appear dimmer than they have any right to be. And for reasons I'll explain later, that meant we decided that they're farther away than they have any right to be. And that suggests that instead of slowing down in its expansion, like any self-respecting universe would, because galaxies are pulling on each other and there's gravity everywhere, so just like this apple slows down on its upward journey, so too we expected the universe to be slowing down and maybe even to reverse its motion and someday to collapse. But what we instead found was that not in this room, not in our solar system, not in our galaxy, but over distances of billions of light years, gravity doesn't dominate. Attractive gravity doesn't dominate. There's some new component of energy in the universe, newly discovered, which we now call dark energy. It has nothing to do with dark matter, and it pushes instead of pulling. And that dark energy is accelerating the expansion of the universe. Moreover, that dark energy is the major component of the energy of the universe. It's fully 3/4 of all that exists. And it's so bizarre that it is thought that an understanding of it will require a unification of the two great pillars of modern physics, the general theory of relativity that deals with things on a very large scale, and quantum physics that deals with things on a very small scale, atomic, subatomic particles, molecules, things like that. And though those two areas of physics work beautifully in each of their respective domains of applicability, when you try to use both theories to address the same problem, you get a tremendous amount of discord. They are in huge violence with one another. They are at war, and there's no common ground. So it's thought that we need someday a theory of everything that brings together both quantum physics and general relativity. And it is widely thought that the dark energy is the most obvious manifestation of a theory of everything. So it's sort of revolutionizing astronomy and physics these days. And indeed, in 1998, it was proclaimed the single most important discovery in all areas of science that year. And there, the caricature of Einstein is surprised, not because he's blowing lots of universes out of a pipe. That's where universes come from. They come from the pipes of eminent theoretical physicists. But rather, I'm just joking, yeah. Rather, he's surprised because this one universe is expanding faster and faster with time, rather than more and more slowly as had been expected. So it's pretty cool, and this stuff is the dominant stuff of the universe, and we don't know what it is. And then there's other stuff that attracts, and we don't know what it is either. The only stuff we know of, really, are the 0.4% of the universe. The stars, gas, us, Cal, lowly Tennessee. Sorry, they're good people, but we beat them finally. Anyway, and then there's another remaining 3.6% that's also made out of atoms, but they're a bit hard to see as well. But anyway, 4% of the universe is sort of stuff that we understand. 96% is stuff that we don't understand. So you can see what an exciting and rich area astrophysics is when we don't know what 96% of the universe is. But we know it's there. We know the dark energy is there, and it's because of this discovery. And so I thought that though I love you guys, I can't pass up a trip to Cambridge to party for several days and stuff. So anyway, okay? So you'll forgive me, but I'll tell you all about it when I come back. All right, I wanted to correct an error I made while rushing at the end of class on Friday. That sometimes happens, like I rush and don't think about things, or a cosmic ray hits me. I was telling you about electromagnetic waves, and that was all fine. And then right near the very end, I said that if you assume that the speed of light is the maximum possible speed, then you get all this interesting stuff in relativity. No, if you assume that, as observations indicate, the speed of light is independent of the observer's motion or the source's motion. So if I measure the speed of light of this laser beam, it's 300,000 kilometers per second, regardless of whether my hand is moving toward it or whether the source is moving toward my hand. All observers see the same thing. If you assume that, as correctly written on my slide, and if you assume that in an airplane you can't tell that you're moving if it's a smooth flight, that is, in a uniformly moving frame of reference, you actually can't tell that you're moving, then you get all this cool stuff. One consequence of which is that the speed of light is the maximum possible speed, and you get E equals mc squared and a lot of other cool stuff. I'll talk about relativity more in the future, but I just wanted to correct that error. Sometimes I say the wrong thing. Okay, so having done that, and having explained that light is an electromagnetic wave, let me move on to the new stuff, and I am 2 minutes behind schedule. Oh, well, that's not too bad. Okay. There's another completely complementary way to consider light, and that is that light is a whole bunch of bundles of energy, little packages or quanta of energy, which go by the name of photons, typically, okay? And if you have a whole bunch of them that correspond to the same color, like red ones, a bunch of red photons, then collectively all these things together propagating along behaves like an electromagnetic wave, and under certain conditions in certain experiments, you see it as a wave. But there are other experiments you can concoct in which you can tell that rather than being a wave, a pure wave, this thing actually consists of a whole bunch of individual bundles of energy. And last year I fell hopelessly behind by going off on a tangent and explaining how it is we know that. It's the birth of quantum physics a century ago. It's fascinating. But why don't I leave it to one of the optional evening bull sessions so that I don't make the mistake that I made last year. But suffice it to say for now that there's a lot of evidence that light is also made out of these particles. So light is both a particle and a wave. And interestingly, it turns out that everything is both a particle and a wave. So is this thing. But this thing is mostly a particle. Doesn't have easily recognizable wave-like features. And a water wave is basically a wave. Doesn't have many particle features. But with light, you can kind of see both aspects of light equally well if you do the right kinds of experiments. So it's both a particle and a wave, but then so are a lot of things. So is essentially everything else in the quantum world. And this, I thought I had pictures of, well, actually, yeah, here it is. This goes back to Einstein and Max Planck. Planck is shown on the right here. And though Einstein never believed quantum physics, he never believed it to his dying day, he was one of the people who actually got quantum physics going, and his Nobel Prize was actually for quantum physics, not for relativity. Anyway, just to tell you a little bit more about photons, they have no mass, no rest mass. That is, if you were to grab a photon and catch it on the fly and try to weigh it, it would no longer exist because, as I will discuss, if you catch a photon, they become absorbed and they no longer exist. If a photon is flying at the speed of light, then it does have energy, but it doesn't have mass. So some people say, well, it has an energy, so by E equals mc squared, it also has a mass. No, it has, in a sense, an equivalent mass, an amount of mass equivalent to the amount of energy it has, but it's wrong, actually, to think of it as a true mass. So a photon is a massless but energetic particle. And the energy of a photon is given by a very simple formula. The energy is proportional to the frequency, nu, or f, script f if you prefer. And the constant of proportionality is called Planck's constant, h. It's very small, and it's named after Max Planck here. But Einstein's analysis of a certain effect called the photoelectric effect was one of the first real strong pieces of evidence for the existence of photons. Planck's argument was more indirect in a sense. So if you look at a bunch of photons, there's ones that go from red to violet, and I've only shown the optical, the visible ones. There are radio photons and gamma ray photons and all kinds of photons. Throughout the whole electromagnetic spectrum, all those wavelengths I talked about last time, there are photons associated with them. Each photon having an energy, h, a very small number, so they're hard to notice, multiplied by the frequency. So individual photons are generally hard to notice because h is such a small number. But anyway, because of this relationship, you can see that the greater the frequency of a photon, the higher its energy. Conversely, because the speed of light is equal to wavelength times frequency, the higher the frequency, the shorter the wavelength. If you have a large nu, you have to have a small lambda for the product to equal a constant c. So if you have a small frequency, like a red photon, then you have to have a long wavelength for the two to equal the same product, okay? So photons of higher energy have higher frequency and shorter wavelength. Photons of lower energy have lower frequency and longer wavelength. So they come in these bundles, and you generally don't notice the bundles, but with gamma rays, it could happen that some gamma ray hits you, and it's like, it knocks your head a little bit. You need a pretty energetic gamma ray to feel it that way, but you could in principle. But regular optical photons, man, who cares? They're just, each of them is so pitifully not very energetic that you hardly care. But if you do the right kind of experiment, you can notice that they're there, and that's really weird. And this was really actually the birth of quantum theory, and you don't have to learn about quantum theory in this class, but I'll do some bull sessions later on in the semester on it, because it is one of the great intellectual triumphs of 20th century physics. The quantum world is a very weird world, and this is one example, perhaps the simplest example of this weirdness. Any questions? Yes? Oh, okay, so the question is, red has the longest wavelength and violet has the shortest wavelength, and if you mix light, you can get certain colors and stuff. Mixing light is a very complex procedure, and it depends on whether you're mixing light that's just going through a room or you're looking at pigments like in a t-shirt or whatever. Mixing colors like paints and stuff gives you very different results from mixing light that's just shining on a white sheet of paper and stuff, and that becomes very complicated. And it has to do also with how your retina perceives mixtures of wavelengths and stuff under different circumstances. Okay, so adding a red photon to a violet photon doesn't suddenly produce a blue one or a green one, okay? There's still a violet photon and a red photon there, and what you perceive depends on many complex circumstances that I don't even really understand very well. It has to do more with human perception, but it depends on whether you're talking about pigments like paints or lights intersecting in a room, shining through like flashlights and a bunch of other things. Yeah, and the colors you see on your shirts and stuff are no single wavelength. They are actually mixtures of wavelengths, and I forgot to bring a little pad of various dyes that I have, which shows, in a sense, the spectrum, the contribution from all the different kinds of photons, giving rise to that blazing pink right there, or that cal blue color, or whatever. None of those is a single frequency light, like I'm showing here in this idealization. All of the lights that you typically see are mixtures. The closest I can come to a single frequency light is this green laser. This is very close to pure light that's made out of green photons and no others. Okay. Anyway, good question, but it's a complex one. Okay, I wanted to introduce photons today because I'm going to be dealing with how photons get absorbed and how we learn about the composition of the universe. So let's go into that. How do we learn about stars? First of all, we're going to talk about stars a lot more later on. But just as an introduction, stars are these giant luminous balls of gas held together by gravity, and they're powered by nuclear reactions going on in the core. And we'll study all that much more later on. And there are a lot of stars, in case you haven't noticed. Just look out on a clear, dark sky away from city lights. But some of you I've talked to grew up in cities and have, for example, never seen the Milky Way. So sometime this summer, go out and look at the Milky Way on a clear, moonless night. This is just a star cluster, but this maybe has 1,000 stars. In a galaxy like our own, there might be several hundred billion stars. And this is not our own galaxy, but our galaxy would look something like this if we could see it from the outside. So clearly an important aspect of all of astronomy is to study stars. But one of the most fundamental aspects you can ask about the universe is, what is it made of and how do we know? The how do we know is as important a part of this class as the facts themselves. Indeed, more important in some ways. So as you will study in more detail on Friday, a star actually emits a continuum of light, sort of like a rainbow like this, and Nicholas will describe this on Friday. But the point of today's lecture is I want to focus in on deviations from that smooth continuum. And the deviations are these little so-called absorption lines, parts of the rainbow, the spectrum, that have a deficit, a relative deficit of light compared to their immediate surroundings. So if you plot brightness versus color or wavelength, that gives you a spectrum, all right, you've got these absorption lines, these dips, and they are produced by atoms or ionized atoms in the relatively cool outer parts of a star that absorb the featureless, that is, no absorption line continuum produced by the hotter inner regions. So these cooler regions, these outer cooler regions, have some bound atoms. The electrons are still attached to the nuclei, and there are different energy levels. And the electrons absorb photons having specific energies, imprinting their fingerprint on the spectrum. And I'm giving you the bottom line in case I fall a bit behind. But the bottom line is that these patterns of lines, and there are thousands of them, I've only drawn about a dozen here, but if you study in detail the thousands of lines that you can see in a spectrum, you can tell that there's like neutral magnesium atoms in the cool outer parts of the star, or singly ionized iron, or neutral hydrogen, or other stuff. And so we can tell that the stars out there are made of the very same kinds of elements that we have here on Earth, which are organized in this very complete and well-understood periodic table of the elements. And we can tell, without buying a star at Ace Hardware, which costs a lot of money, you can tell, even though they're hundreds of light years away, what they're made of through this technique of spectroscopy. By spreading the light into a spectrum, measuring where the absorption lines are, and comparing those wavelengths or frequencies with the measured wavelengths and frequencies of gases in ground-based laboratories, where you can measure what the transitions are between the various electrons in neutral magnesium, singly ionized magnesium, neutral iron, singly ionized iron, and so on. And so this is how we know, a very fundamental thing. And the rest of this lecture is about the details of how we know the composition, how we know that there is oxygen out there, for example. Okay? All right, so that's that. So let's get into a discussion of more details. So as you all know, this is review. Everything is made of atoms, and the atoms, as we discussed last week, are mostly a big cloud of electrons within which there's a bunch of empty space, and somewhere way down in the middle, or near the middle, is this little tiny nucleus. But 99.99999% of the atom is empty space. A typical atom might be 1 angstrom, 10 to the minus 8 centimeters in size, 1/100 millionth of a meter. No, sorry, of a centimeter, sorry. 1/100 millionth of a centimeter, that's 1 angstrom. But most of it is empty space. The nucleus is this little tiny thing consisting of protons and neutrons, each of which is something like 10 to the minus 13 centimeters in size. Now, the protons are positively charged, the electrons are negatively charged. There are equal number of protons and electrons for a neutral element, okay? Then there are the neutrons, which help bind together all these protons, because if you just had the protons, they would repel each other because they're all positively charged. So the way you keep them together is having a bunch of neutrons there, which adds some so-called strong nuclear force. And we will discuss that in the context of cosmology later on. But that's what good the neutrons are. They help keep the nucleus bound. Okay, well, the electrons are these little tiny things about 1/2000th of the mass of the proton. You don't have to memorize any of those numbers. So I think this is a familiar picture to people. What may be not quite as familiar, although I think it is that these electrons can't take on any old energy that they want. They have only certain allowed values for the energy, only certain allowed energy levels. In high school, you might have called them orbitals or orbits. Quantum physicists don't like that term because it suggests that electrons are like planets circling around the sun. In this case, circling around the nucleus. That's not the way they're doing. They're actually cloudy so-called probability distributions in the quantum mumbo jumbo, which is actually fascinating, but it's not the place in this lecture to go into all that. So they're not really orbiting. Nevertheless, they have preferred energy levels that correspond to certain distances from the nucleus. And you simply will not find electrons in an unallowed energy level. It doesn't exist, and you won't find them at that particular location corresponding to that energy, that hypothetical energy level away from the nucleus. So here's a hydrogen atom, for example, and the simplest energy level is this one that's closest in, and it's basically spherically symmetric, but not all energy levels have this spherical distribution. Some are much more weirdly shaped. You may have in high school studied SPDF orbitals. That's great if you did. Don't worry about it if you didn't. You won't need to know them in this class. But here, very simply, I've shown the simplest element because all the concepts, or most of the concepts, can be discussed with the simplest element in mind, and all the other elements are simply more complex examples of that. But here's hydrogen with the electron drawn in its allowed energy levels, or orbits, or orbitals. But again, I put that in quotes because I don't personally like that term. So basically, you'll never find the electron here because that's not an allowed state. You can find it there, the ground state, or at progressively higher energy levels. The second one, or the first excited state, the third one, or the second excited state, and so on. So it's kind of like a parking meter, okay? You can have these parking meters, and you can stick in a nickel, a dime, or a quarter. You can't put in 17 cents. It's simply not allowed, okay? So if some guy on Telegraph Avenue asks you for 17 cents because he needs to feed the meter, you say, nope, 17 cents isn't allowed. All right? That's what you should say. Anyway, give them food, I say, not so much money, because they'll spend the money on other bad things. Anyway, I'm not here to give you a moral lecture on that. The point is that you've got these levels, and it's like a parking meter. Certain combinations aren't allowed. Certain ones are allowed. All right? So you throw 17 cents at a parking meter, and it just ignores those 17 cents. It doesn't take 15 of them unless you put in the 15 and save the pennies, for later. But you can't do that with photons, it turns out. The atom either recognizes the photon or it does not. And it recognizes the photon if the photon has an energy which corresponds to one of the allowed transitions between wherever the electron happens to be and one of the higher energy levels. If an incoming photon encounters an atom and it has the right energy, it'll get absorbed by the electron in that atom. If it doesn't have the right energy, it'll pass right through unimpeded. It's like you throwing the wrong amount of change at the parking meter. So here's a photon coming in, and I've drawn it so that it has exactly the right energy to kick an electron in the hydrogen ground state from the first energy level to the third. And I've drawn it violet because actually it turns out that this transition requires an ultraviolet photon. But your eyes don't see ultraviolet very well, so I did the next best thing. I drew it violet. Okay? So these outer levels have greater energy than the inner levels. So if the atom accepts the photon gets absorbed, the electron jumps to the higher energy level, and in the process, the photon ceases to exist. The photon no longer exists. It was eaten by the electron in the atom. And now the atom is in a higher energy state. Now, electrons in a high energy state are lazy creatures. They like to jump down pretty quickly to lower energy levels. In so doing, they can emit a photon. They can jump down back to the first level, in which case they re-emit a photon having exactly the same energy as the one that came in, or to within quantum effects, exactly the same energy. I won't get into that right now. Or maybe the thing could go to the second energy level first and then the first energy level, and it would emit two photons, the sum of whose energy is equal to the energy of the incoming photon to begin with. But you can't end up in a state halfway between, and the electron can't take part of the photon's energy, knock itself up to this level, and emit the remaining energy. It just doesn't do that, okay? It either takes the whole photon or it rejects the whole photon. All right? So if you had a whole bunch of light having different colors shining on a bunch of hydrogen atoms, and in this case I've cleverly put the electron already in the second energy level because it works out better that way. But suppose it's already in the second energy level rather than the first. It makes no difference except for the colors, and I wanted the colors to correspond to real life. Then all these, red, green, blue, and violet guys, all these photons are shining through the gas, but the green ones, or at least some of the green ones, will say, hey, I've got just the right energy to be absorbed by this electron and be kicked up to, in this case, the fourth energy level. Now, you don't have to memorize this, okay? But it so happens that a hydrogen atom with an electron in the second energy level can get kicked up to the fourth energy level by absorbing a green photon. Not just any old green photon. It turns out it has to have a specific frequency. Green is a rather loose category, So it turns out it has to be a very specific green one. But nevertheless, it's a green one, and here conceptually this will suffice. So that green photon had an energy of the photon, equal to the difference in energy. This capital delta is usually used in physics to denote a change or a difference in two quantities. It corresponds to the difference in energy between the energy of level 4, that level there, and the energy of level 2. Remember, the outer levels have greater energy, so this is a positive difference. And that energy difference is equal to h nu, looks like a V here, sorry about that, but it's h nu of the photon, and since lambda nu equals c, nu is c over lambda, so I could just as well say hc over lambda photon. You should become comfortable with that kind of a thing. And what comes out then is the same light that you were shining on the gas, but the green photon is now missing, and lo and behold, the electron finds itself in the fourth energy level. Okay? So that's what happens. Then, as I said, once the thing is up there, it's pretty lazy. It likes to hop back down to a lower energy level, and it does so quickly, just a fraction of a second later in general. But the emission of the photon can occur in any direction. It is not necessarily the direction in which the light was going to begin with. So, once this guy hops back down, he'll emit in this direction or that direction or that direction or that direction. So it's still the case that of the bundle of rays going in that original direction, the green one in general will be missing. Because even if the photon got re-emitted as the electron hopped back down, in general it's not emitted in the same direction in which it was usually going. And so there's a deficit now of photons in the direction in which they were going. And if you were here, down here, and measured the spectrum of this star here, you would notice that the green photons, or at least some of them, are missing. Not only is it the case that the photon can be re-emitted in any old direction, but it can be a succession of levels. Actually, here I had it not going down to the second energy level, I had it going down to the first. But it could go to the third, and then to the first, or it could go to the third, then the second, then the first, or it could go directly to the first, or it could go to the second, and then the first. In other words, the upward transition is followed by a number of other transitions, several jumps. And if several jumps occur, then the energy of the original photon gets re-emitted in two or more lower energy photons. Now, let me give a demo. So there's no slide here. I've got this chair here, and I've got this step right there. So let's call the step that I'm on there the ground state. And let's say that going up to this next level, n equals 2, suppose that requires a red photon. And suppose going from here to here requires a green photon. And let's suppose that the energy levels are set up in such a way that the energy of the red photon plus the energy of the green photon is exactly equal to the energy of a blue photon. Okay, this is a hypothetical atom here, okay? All right. So, I'm going to stand here and, what's your name? Peter. Peter, why don't you toss me that red photon? So Peter tosses me the red photon, and I hop up to the next level up. Oops, I should have distributed here. I'll give him a bunch of here, Peter again, and then you are Brittany. Stephanie. Peter, Brittany, and Stephanie. Okay, so Peter, let's do it again, dude. All right, so I jump up to this one. Now, Brittany, toss me the green photon, and I jump up to here. Oh, shoot. Stephanie, can you give me the blue one? I meant to have it. Sorry. Just go ahead and give it to me. Now, I should do something here. I should hop off even higher, but I won't. Now, having gotten to this energy level through the successive absorption of two photons, a red one and a green one, I could now hop down to the lowest energy, and what should I emit? A blue photon. So I'm going to give it to Stephanie there. Oh, bad catch. Actually, it was a bad throw. So now, Stephanie, why don't you try throwing me the blue photon? All right? I can't catch. Lucky I'm not on the football team. Anyway, what should I do? Go zipping up to the top level, okay? Now, some years ago, I was up on this level here, and I think I broke it or something, but I jumped down on another chair, and it was one of these foldable, collapsible chairs, and it collapsed, and it broke, and a sharp part hit me in the rib, and the pain lasted for like several months, so I concluded that I cracked a rib. I don't think I broke it, because I couldn't feel anything kind of moving around randomly in my kidney and stuff, but anyway, but it was right near the end of class, and people on the webcast were all like, you know, are you dead? Are you alive? Like, if I'm dead, I can't answer the email. But anyway, so now suppose I were down here, and what's your name? Katrina. Katrina, throw me a yellow photon, okay? Nothing happened. Not because she missed, but why did nothing happen? It's the wrong energy, right? Okay, there you go. It was the wrong energy to be absorbed, because what do I need to get up to this level? A green photon, right, okay? Now, you know, there might have been some other energy level that would have accepted a yellow photon, but not the way I made this hypothetical atom, okay? So you can do this at home. You can illustrate physical concepts, you know, play with your balls and illustrate physical concepts, and, well, you know, you can learn some physics this way, really, and just make sure you play with your own balls and not someone else's balls. But anyway, I like this kind of stuff because you can do it at home without you know, spending a lot of money, okay? You can think about these kinds of things, and I'll talk about this a little bit more later on. I have a few more related demos, okay? So it's a great way to learn some physics, okay? So the point here is that in this case, I set up the atom so that the absorption of a green photon would give rise to that transition there. By the way, once I was up here, I threw Stephanie back the blue photon, and I hopped down to the lowest energy level. What could I equally as well have done? Green and then the red. There you go. What's your name? Chris. Okay, Chris says green and then the red, not red and then the green, because by emitting a red photon, I'd end up in some never-never land, right? I wouldn't end up in an allowed state. So yes, I'll throw Chris a green photon. Oops, I landed in the wrong level, right? I should have gone to here, and then I'll throw Peter the red one, since he likes the red ones, but he doesn't like the color red too much, of course, right? Or if he does, he doesn't admit it. Okay, so that's that. Now, if you take a spectrum, as I was saying, of this light from a source that emits just a continuum, let's say, all right, you take a spectrum of it, you'd get this smooth continuum, but some form of green light. And it looks like on this slide, somehow my scale here got shifted a bit. Looks like it's between green and yellow. But anyway, this absorption line should be sort of right above the G for green. I don't know if it is in the reader or not. No, seems to have shifted. Okay. Anyway, the point is that one of the particular wavelengths of green is now gone. And in general, a gas doesn't just have a simple hydrogen composition. It has other things as well. And each of the elements gives rise to its own particular pattern of absorption lines. And the strongest lines in the spectrum of the sun were studied by a guy called Josef Fraunhofer, and they're called Fraunhofer lines. But if you look at a detailed spectrum of the sun, there are literally thousands, tens of thousands of lines differing from each other only a little bit in wavelength. So I drew a big broad thing here that's just, I called it nominally green, but you know, the range green could actually have many, many slightly different absorption lines having slightly different wavelengths, and I'll show you an example of that in a minute. Now, there's one other process that can occur, and that is that if, let's say, what's your name? Hallie. Hallie, throw me a violet photon. Oh, sorry about that. You don't have to throw it violently, but you can throw me a violet photon. Meant to do this. So, Hallie, go ahead and throw me, oh, and by the way, this is the nucleus of the atom here. This is the proton here. So now just throw it to me. This photon has such a high energy that it doesn't get me to any of the allowed bound energy levels. So now I'm a free electron. I'm no longer bound to yeah, making it difficult for the camera guy. But anyway, I'm no longer bound in any particular energy level. I'm no longer bound to the atom. I'm free. And any photon with an energy at least as big as what is needed to ionize the atom will do so. In other words, you don't need a precise energy to go from a bound state up into some unbound state, because any energy at least big enough to get the job done will suffice. But if you're going from a bound state to a bound state, then you need a particular energy. And then, going back to this, there's this joke. It's really lame, but two atoms are walking, down the street next to each other, and one says, "Hey, I think I've lost an electron." Or he says, "I'm an ion," or "I've lost an electron." And another one says, "Are you sure?" And the first one says, "Yeah, I'm positive." Okay, right? Because after you've lost an electron, or if you say, "I'm an ion," then yes, I'm positive. Anyway, it's really bad. But okay, so I just did that demo. There is, it turns out, one more way that you can ionize an atom, and this will be more relevant later, but since we're into doing demos right now, instead of throwing me a photon, Peter, why don't you kick me? Just kick me really hard, okay? If you kick me hard enough, that's not very hard, but you want to get an A, then I can also wander around. So electrons can be kicked up to higher energy levels under certain circumstances, or if the collision is violent enough, they can also be so-called collisionally ionized. But I just thought I'd mention that for completeness. That has nothing to do with the absorption lines that we're talking about in this lecture, but it will be relevant for later in the course. Okay, so I have 6 minutes to bring it all together and show you a few examples with a cool little animation. So the bottom line, and again, like looking back in time, this is going to be one of the key things you'll ever learn in this course. Question. Very good question. The question is, if a photon of light having the right energy encounters an electron in an atom that could, in principle, absorb that energy, does it have to? No, it doesn't have to. It's a quantum mechanical probability. And theoretical and experimental physicists study the various probabilities of a transition actually occurring given conditions conducive to its occurrence. And some transitions are very unlikely, and some are more likely than others. And it's a very complex thing. That's a good question. Okay, so the bottom line is this, and this will be great, because in the next 5 minutes I can really bring this all together. Key thing, how do we know that the stuff out there is made of the same kinds of things as here on Earth? Someone might ask you that, and you might say, I don't know, I was told that the stuff is the same throughout the universe. Now you can tell them how you know. The point is that each neutral element or ionized version of an element, whether it's lost one or more electrons, produces a unique set of lines. So any particular wavelength, if you see a line, you might not know what that element is that produced that line. But it's the patterns that are unique. And I show you here hydrogen, not because you need to memorize it, but because it's the simplest. If you go from n equals 1 to 2, 3, 4, 5, 6, 7, and so on, that requires ultraviolet photons of a particular energy, and that's known as the Lyman series. Don't worry about that. I'm just giving you the terminology just for kicks. If the electron is already in the second excited level, suppose it already absorbed a so-called Lyman alpha photon and got up to here, or suppose an electron collided, like Peter and me, and knocked the other electron up to a higher energy level. So it starts out from here, but then it can absorb photons to the third, fourth, fifth, sixth, seventh energy level, and so on. Those are called the Balmer lines. Those are the optically visible lines. Or you could start out in the third energy level and go up to the fourth, fifth, or sixth. Those are called Paschen. Those are in the infrared, and so on. There are other infrared lines. But because of the spacing, which I've drawn approximately correctly here, the spectrum of hydrogen, again, not to be memorized, just get the gist of what I'm saying as an example of a more general process. The spectrum, the brightness of light versus wavelength, light that has gone through hydrogen gas some of whose electrons are in the lowest energy level, some are in the first excited state, some are in the second excited state. So suppose you have hydrogen gas with all possible states already populated, you will get all these absorption lines. The ultraviolet ones, the Lyman series, the Balmer ones, the visible ones, sometimes just called H alpha, H beta, and so on, and the infrared Paschen lines, and so on. And a trained spectroscopist, boy, you know, don't say that word too close to someone. You might spit all over them. People in the front row already get sprayed by my generous portions of saliva come flying out of my mouth. But anyway, that's tough for them. But anyway, a trained spectroscopist recognizes these patterns and says, look, there's hydrogen in that gas, and I know it because no other element or ionized species of an element produces exactly the same pattern. Okay? That's how we know. And all other elements or ionized species of those elements produce different patterns, and by looking at the patterns in the spectra of stars, we can tell their composition, or at least the composition of their outer, relatively cool layers. So not only are there the strong so-called Fraunhofer lines, but if you really spread out the spectrum a lot, really spread it out a lot, then you can see the plethora of little absorption lines. Some are big fat things like that, strong ones like that, and some are weak little things like this. A lot of these are iron. This is a spectrum of the sun. A lot are calcium and other things, magnesium, iron, scandium. We can tell what elements are there and what their ionization state is by studying the patterns in great detail. And what I wanted to show you was an example of this. Here's a little applet where it shows the spectrum of a star, assuming there are no relatively cool elements in its outer envelope. So then you just get a continuum. The shape of that continuum will be something that Nicholas will describe on Friday. Okay, it's a thermal emitter, it's a black body-like thing, okay? But now let's suppose I turn on, I say there is hydrogen in the right energy levels. See that? Some absorption lines turned on, okay? Now I can turn off hydrogen, and watch, helium will have a different pattern. And you will see this in discussion section next week. We'll have a little demo. And carbon will have yet another pattern. And calcium has yet another pattern. And oxygen has another pattern still. And magnesium. These are just the neutral forms. I haven't even shown the ionized forms. There's iron. And if you turn them all on, you might think it's a hopeless mess. But a trained spectroscopist can tell from this jumble of lines what patterns are there. These are the fingerprints of atoms. And in fact, you can even tell how much there is, because if you vary the amount of hydrogen, for example, some of the lines weaken. The hydrogen lines weaken with time. I'll show you that perhaps more later. And similarly, if you look at glowing clouds of gas, you can also tell what they're made of. Because if you look at a glowing cloud of gas from the side, you'll see the very same photons that the atoms emit upon having absorbed photons from a nearby star. So in this direction, looking at the star, you'll see an absorption line in its spectrum. But if you view the cloud of gas from other directions, you'll see the photons that that cloud of gas is emitting in random directions. And this is what makes a cloud of gas like the Orion Nebula glow. You can see the different elements in the spectrum of the Orion Nebula. And so the bottom line, this is how we know of what the universe out there consists. Okay, I'll see you next Wednesday. Thank you. Yeah, sure. Yeah. Yeah. Well, your eyelashes and also the optics in your eye spreads out the light in a way that's dependent a little bit on the wavelength of the color. So yeah, and you can tilt my head. Sometimes I think it's my eyelashes because if I close my eyes in a different way, the pattern shifts and stuff. But yeah, 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 it's spreading it out a little bit. That's right. Right, Nicholas. Here for you is this. Okay, and I will take the basketball. Yeah, where'd it go? grab the basketball. Oh, here it is. The official NBA basket small. And here's a plastic bag in which you can put the ball. And I left off exactly where I wanted to, so you are all set. Okay? Yeah, hi.
I just have a question about waitlisting. What are the chances that we'll be...
You'll get in for sure.
Okay.
In fact, there's room in the course right now if you just sign up for the right discussion
I signed up
section.
for it today.
Yeah, if you're,
Okay.
you're waitlisted not because the class is full, but because one of the discussion sections to which you tried to sign up appears to be full. But if you search for some other discussion section, you'll get in right away. But if that's the only one that's convenient, don't worry about it. I'll let you in. Okay? Yeah. Okay.
I
Hey.
missed the first few minutes of lecture, but
Yeah.
you said something about the Lick Observatory.
Yeah. Why don't you?
I already wrote the essay. But
Oh, you did? Okay. Not yet. I'll lose it because I'm about to go to England.
Yeah, yeah,
But
after.
turn it in. Wonderful. So you read page 9 in the course reader then. Excellent. What's your name? Orion. That's a great name. Gotta shake your hand. All right. Yeah. Hi.
I had a quick question. Can you tell the age of the star by looking at the spectrum?
Not in general. Getting ages of stars is considerably more difficult, and I'll tell you how you do that later. But the bottom line is we do it by looking at clusters of stars, and we can tell how old they are by seeing which star masses are no longer present, because the more massive stars burn out more quickly than the less massive stars. So by seeing which ones are present, which ones are absent, you can tell how long the cluster has been in existence. Yeah. What's your name?
Felicitas?
Oh, it's a great question. Say it again.
Felicitas?
Felicitas. Okay,
Yeah.
great. Very good question.
I was wondering because you said before that